Hello everyone, and thank you for joining us today. We're excited to bring you this overview webinar on Design and Operate, a continuous digital twin journey. The ETAP Digital Twin is an integral building block in all stages of an electrical system's life cycle. You can leverage the ETAP Digital Twin to not only shorten design time, but also validate and transition this digital twin into operations. Once it's in operations, you can then use it for early decision support, identification of operation problems, and also identify the root causes. You can also leverage it to accelerate engineer and operator training and asset performance monitoring and optimization. So let's go ahead and get started and learn about digital continuity in design and operations. The industry is facing a number of challenges when it comes to modeling, design, and operations. So let's quickly revisit some of these challenges and the solution that the digital twin provides. One of the number one challenges in the industry when it comes to modeling is the prevalence of multiple softwares. So ETAP solves this by essentially providing a single platform with over 150 different modules that can be leveraged in an integrated or comprehensive database. ETAP also includes data revisioning that allows you to keep multiple instances of your project, especially time series changes, in a common or single database. ETAP NetPM allows you to centralize distributed copies of the project model in one central location and keeps it synchronized. So therefore you can track who is doing what and give you some level of control management, as well as allow you to perform the project activities in a simultaneous manner versus the traditional sequential process of doing load flow, then short circuit, then arc flash, and so on. With ETAP, you can perform all of these studies in parallel. When it comes to design and analysis, there are also a number of challenges, and ETAP provides the appropriate solutions. One of the common challenges that we run into on design and analysis is opposing study goals, where load flow, short circuit, arc flash, protection all take us in different directions based on the outcome of each study. But by collaborating together on a single platform, you can essentially find out all these opposing goals and resolve them in a collaborative manner. It also therefore allows for simultaneous engineering efforts and avoids a more traditional sequential process of conducting power system studies. ETAP also allows you to create, simulate, and analyze multiple scenarios. Therefore, you can analyze many different combinations of information in a quick, concise, and precise manner. And this essentially not only helps you create scenarios for design and analysis, but then leverage these scenarios later on in the future for operations. Having over 150 different modules on a single platform also allows you to run analytics or analysis for any given sector. For example, if you are analyzing an airport electrical system, you can leverage GIS, you can leverage eTracks for automated people mover systems or train systems within the airport, data centers that are within the airport itself, medium voltage, low voltage, renewables, all in one single electrical system model. Having scenarios allow you to repeat the studies over and over again in a single click. And this is particularly useful whenever you are faced with a change of input data and you need to rerun all your studies and generate your deliverables in a quick manner. Finally, accuracy and dependability is key for any design and analysis tool. So ETAP also includes verified and validated libraries for engineering devices. And of course, the entire software has been certified for nuclear use since 1991. When it comes to operation and automation, traditionally, operation and automation has been disconnected from design and analysis. And this is because the single line diagram prepared during the design and analysis phase was essentially kept aside, and a new HMI was constructed, allowing you to visualize and operate the system. But this HMI lacked the electrical connectivity and all the knowledge that was put into the design and analysis model at the time the system was either constructed, designed, or expanded, especially in a brownfield situation. ETAP bridges this gap of design and operation by allowing you to utilize that real-time data all the way from design to operation to automation, which is the focus of this webinar. We're doing this on a unified platform, and all the scenarios that were prepared during design and analysis are available for operations and engineering. Operation optimization becomes an automated process leveraging this digital twin, and the automation confidence challenge is solved by validating the operation side while you're doing your design. And we will talk a little bit more about this later on in this webinar. And then also the digital twin can be used to give the operators better operation familiarity by essentially leveraging that twin for operator training simulator. So what happens if you continue using a multi-platform, non-unified lifecycle? It essentially has a negative impact on your project lifecycle and its delivery timeframes. The project goes through a conceptual stage into detail engineering and then into operation and maintenance. And this is where we want to ensure that the data that is put together during conceptual stage carries all the way into operation and maintenance. And there are no barriers that are placed for this data to flow. If the barriers exist because of a multi-platform, non-unified lifecycle, those barriers essentially lead to errors and omissions of data. It can lead to rework, essentially where you are re-entering the data that you do not need to. It could be simply reused. And that tends to lead to lost time, project delays, and then indirectly increases the cost of the project delivery. So therefore, these silos or walls are to be broken down and the digital twin to be translated all the way from design to operations. ETAP now serves over 10,000 companies, and based on our customer feedback, which includes the staff hours and the cost avoidance of using a process like this, our customers are able to improve design efficiency, avoid costly errors, and eliminate uncertainties. So the ETAP Digital Twin essentially allows us to design with automation knowledge, where we can conceptualize the model with accurate design device characteristics, and that may result in about 5% savings in time and cost. By analyzing the system with renewables and microgrid controllers, you can further optimize that design and have a saving of almost about 8%. And that same digital twin can now operate with the system design knowledge. So when that happens, you are able to commission the system, essentially validate before energizing, and avoid costly disruptions, and could tend to lead to about 5% additional savings. When you automate that system with the design model and the characteristics, you can now apply optimal control and also generate a more experienced operator training program, and that may lead to an additional 3% savings. You can then utilize the optimization capability within ETAP for condition monitoring and failure analysis and do optimal maintenance of your assets. And that could lead up to another estimated savings of about 2%. So by going from design to automation and then operating with the design knowledge, you can essentially have an estimated savings of almost about 20% using a unified digital twin that's moving all the way from design to operations. So with that digital twin, you can not only record the past, where we are designing the system, archiving the data, visualizing the past, but you can also understand the present by bringing in operations data and analyzing the what if cases and use it for education purposes for the operator. But you can also predict the future by allowing the controllers like microgrid and power plant controllers to operate the system with look-ahead capability and forecasting capability to better optimize and manage the electrical system. So total engineering and operation can be achieved over a single digital twin that spans all the way from design into operations. So let's drill in a little bit more and see how ETAP completes your end-to-end journey. The digital twin state is usually as designed when we are analyzing our electrical system. We are modeling the electrical single line diagram, and we are conducting load flow, short circuit, power quality, arc flash, and many different kinds of studies. This can be done in the conceptual and detail engineering phase, and the value that we extract from that model is the analysis of the electrical system. Now bear in mind, we don't want to lose this value, we want to retain this value all the way into operations. So as we move further along in our journey, the ETAP design model now connects to another ETAP model, and together in tandem, they are performing a software in the loop simulation. And the digital twin now is in the as predicted state, where we can leverage it for factory acceptance test. In other words, I'm validating the performance of the model and the control system as designed before I'm moving into operations. And I'm using that to validate my control knowledge that I've put into my original ETAP design. That control knowledge can include microgrid controllers, power plant controllers, everything that was incorporated right up front in the design stage itself. When we get into handover and commissioning of the electrical system, and this is particularly important for EPCs as well as for end customers, you can use that model for operations simulation. So this model now becomes an as trained model where the operators as well as the EPC or the end user are using it to learn what happens as they energize the system. Not every system is energized in one shot. It is done over a phased manner, and this helps you understand what the impact is going to be as you energize each stage. Remember, in detail engineering, there may not have been any cases analyzed for a handover or commissioning stage. The same model now moves and becomes a basis for operator training simulator. So it stays in the as trained state, but now it's in the hands of operations. And now they're using this to gain experience. They have learned how the system behaves. Now they're gaining experience by leveraging the real-time data along with this digital twin model and replicating certain scenarios that happen in actual operations. And ETAP real-time then takes this model and pushes it to the next level, where this model becomes as operated, it can become as forecasted, it could be as optimized, as predicted, even as recovered and investigated, which means we are also using it for forensic analysis, for look-ahead capability, to optimize settings such as tap changers, capacitor banks, and so on, for forecasting the load and generation, and then of course validating certain actions before we take those actions in real system. In other words, validate before operate. And this is where we gain situational intelligence, where the design scenarios that were constructed during this phase are being leveraged for actual operations. Therefore, ETAP solves your challenge by taking this digital twin model all the way from design into automation. And where can we leverage this? We can use this to modernize our electrical system for more effective and efficient control management, such as microgrids and renewable power plants. Ensure safety and reliability by making sure that you have a model that can predict accurately what the impact is going to be before you operate the system in a certain manner. Maintain resiliency, so essentially the recovery of the system after a disturbance that is unavoidable. Maintain compliance with the grid connection, whether it is grid interconnection compliance or grid operations compliance. And then finally, reduce the overall carbon footprint or carbon neutrality by ensuring that the control systems are optimally behaving or working along with the renewable and energy storage devices you may have in the system. So as we move further along, we'll talk about design and analysis, monitoring and prediction, operation and optimization, and automation and control of the electrical system using a single digital twin on a unified digital twin platform. Now, in order for this digital twin platform to serve all of these different functions, it must have a lot of flexibility. It must have the flexibility of graphical visualizations. Therefore, ETAP provides unlimited graphical visualizations of your single lines, GIS, protection selectivity, SCADA, and so on and so forth on a single platform. It must have data revisioning, where you can not only revision future information, but also have control over what real-time data is being pushed into that electrical system model. There must be flexibility on configurations. So configurations that are used under design stage may be quite different than the ones that are used during operations. So the visualization, which we call presentations, the configurations, which is the topology, and the data revisioning, which is the state of the engineering data, are all unlimited within ETAP. And then we overlay on top of that sequence of changes. So this could be changes as a function of time, or essentially forecasted information where loading and generation is being modified above and beyond the visualization, revisioning, and configuration. So this gives us a complete multi-dimensional or a four-dimensional system where we not only have the spatial data but also the temporal data in a single database. So let's take a look at the what-if scenarios in action. You can simply run a study within ETAP, any study for that matter, and pick between any of your current configurations that you may have defined in the system. The configuration may include breakers that are open and closed, and whenever a part of the system is de-energized, it's shown in that gray color. Now you can take multiple presentations together, side by side, set one configuration in normal mode, run your study, run a study on the parallel presentation in a different configuration, and here we can see the impact of having or not having wind turbine in the electrical system. Again, the de-energized wind turbine is shown in this gray color. You can also pick from different scenarios that you may have already created. These are user-defined, unlimited scenarios, and analyze them. You can also put n number of scenarios into a batch. For example, a load flow scenario batch or a short circuit scenario batch, and run these scenarios step by step in an automated fashion. And this way you can spend more time performing the analysis of the electrical system rather than focusing and spending time running the simulation. Once the scenarios are created and you have analyzed them on a particular presentation or in a particular view, you can also leverage revisions. So the revisions essentially let you view the changes in that particular phase or that particular year. The changes are shown in this green color, so you can quickly go to a particular component, make a change or view the change, and analyze the system as if it is in a future state. You can also essentially get the results of a generator, in this case being changed from 3 megawatt to 10 megawatt, and see the impact on the electrical system. Based on that impact, you can then perform additional optimization of the electrical system design, its protection, without affecting the as designed case. In the as designed case, this generator is still a 3 megawatt machine versus phase 1 where it is a 10 megawatt machine. And we have two different sets of results that you can always compare through the analyzers. We essentially also allow you to put the views side by side. And the reason for doing this is so that you can also have different symbology and a different representation of the electrical system. So the look and feel of the single line diagram or your geospatial diagram can be different from one view to another. You can have a view where you have relays displayed in one presentation, but they're absent in the other. But they're all being derived from a same single common database. So now that we've looked at our multi-dimensional digital twin platform, which is the foundation or the fabric of our design and operations solutions, let's take a look at the journey itself at a more macro level as we then drill deeper into each of these pieces. Now, depending upon which segment or sector that you're dealing with, whether it's industrial, T&D, substations, renewables, power generation, data centers, manufacturing, microgrids, you always will begin at this multi-dimensional modeling stage. We will then always transition into design and planning, where we have a number of solutions for different segments. Then we essentially have advanced design and planning solutions. Again, depending upon the segments, these may vary. And then we commission our system, where we have different solutions as well. Once the system is commissioned, we want to get into operations, and then we start engaging power, energy management systems, ADMS for distribution systems, PPCs or microgrid controllers for renewable, and substation automation for transmission, distribution, and substations in general. And there are many different journeys that you can go through, but this is sort of the basic foundational way of moving from design all the way into operations. And each segment may take you in a different journey, but the basic principle or the philosophy remains the same. So our unified digital twin platform allows us to collaborate and push data into the model through the cloud or through a mobile app, through which we perform analytics, and then we essentially generate deliverables. That includes the single line diagram, the geospatial diagrams, reports, plots, and so on. We can also supplement data into this digital twin model through other third-party vendors and other formats. For BIM modeling, you can interface with Revit. For distribution systems, you can integrate with Esri or OpenStreetMap, or have data come in through Excel, and many different approaches. You can also bring in DWG or CAD files directly into ETAP and auto-generate that single line diagram. We are then enriching this model with protocol information. And what we mean by protocol is essentially that real-time data that comes into this model through IEC 61850, DNP3, Modbus, SIM, or ICCP, or any other industrial standard protocol. And then when we combine all this data together in our digital twin model, and we are leveraging the presentations, the configurations, the revisions, and the time series changes, we can generate unique solutions for each sector. So let's take a look at the value that this digital twin brings to our customers, and how does it go about its complete journey from design to operations in a bit more detailed manner. So this model, that is a multi-dimensional model, includes low voltage, medium voltage, high voltage, AC/DC, as well as balanced and unbalanced systems, radial or meshed, all implemented together at any voltage level, at any frequency, combined together to form a complete connectivity model of the electrical system. This model is then collaborated upon by utilizing NetPM. Again, this is where multiple engineers can work together to either enrich this model or perform analysis on it. The analysis is performed using various different visualization of the electrical information, which could be through geospatial data, schematics like a one-line diagram, net views, which is a simplified substation connectivity view, or feeder views, where you're just looking at a single breaker or a single feeder that leaves the substation. This model data is improved by the ETAP app, where your field electricians can go out, collect the data, and automatically synchronize that back to the model and validate some of the key information. In case the data is coming in a manner that is not carrying any geospatial or logical coordinates, there's also layout routines within ETAP that automatically lay out the single line diagram based on user-defined rule books. Many times the loading information is unavailable, so if you do have existing measurements from the field, you can plug them into ETAP and allocate the meter measurement all the way down to the load in design stage. So therefore your analysis is based on normal loading levels of the electrical system and not overly conservative in terms of doing the analysis. And then finally, there's model validation tools that we can leverage to make sure that this model, what it's predicting, is validated with actual field measurements. And that essentially is our journey for our multi-dimensional modeling phase of the project. When it comes to the visualization, as I mentioned earlier, we have the one-line views. You can have SCADA alarming views, SCADA HMIs, web dashboards, network views, as well as geospatial views, all being derived from a same single common database or multi-dimensional database. NetPM, as I mentioned earlier, has the ability to be established on the cloud, or it could be hosted on premise. that allows ETAP desktop client, the ETAP app, and any other desktop client to essentially collaborate together and exchange data amongst each other. And this again helps us change our delivery time schedules. So this is what a typical power system project schedule looks like without NetPM, where you are going through the modeling phase. We go through the model validation phase where we get operations data for a single snapshot of information. And then we compare it with the load flow result and validate our load flow. And then we actually perform the load flow calculations and equipment sizing, short circuit duty sizing, selectivity, arc flash, and so on and so forth. And this takes weeks to months to perform. And with NetPM, we're essentially looking at a much shorter delivery time frame where you can take certain tasks and put them in parallel. So therefore, any number of clients, whether it's the mobile, desktop, can collaborate together from any part of the globe, depending upon the location of this NetPM server. The ETAP app, which is a key component for data collection, allows you to not only visualize the model on the app, but it also allows you to take that app out in the field, get the location of the asset, get additional metadata like photos, schematics, and so on and so forth, and plug them into the app, and then synchronize this with the actual ETAP Digital Twin model. So again, you can go in parallel in terms of validating the data and enriching that digital twin model. So as far as the field data collection itself is concerned, you can just simply tap on a component, take a picture that you've already captured or capture a new one using your camera, type in the description, and essentially make it part of your digital twin information. It's particularly useful when you are not sure about certain amount of data that you're collecting, what it means, and you want to go back and refer back to that piece of data again without really going back onto the field. The app also allows you to edit the data directly on the tablet itself, where you can automatically insert components, select a component, modify the data, or copy and paste the data from one component to another, making it quite quick and easy to create new objects or assets in the tablet itself and then synchronize them with the model that you have on your desktop. This again speeds up the model building exercise and makes it quite efficient as well as accurate in terms of data collection and data quality. When it comes to the design solutions, we can leverage the rulebooks and engineering libraries that we have within ETAP that allow you to design the system in confidence. So you can then start performing load flows, short circuits, protection selectivity, AC/DC arc flash, the cable system computations such as sizing, thermal analysis through underground raceway system, substation ground grid safety, and then leverage the evaluators and analyzers and the study results to sort of consolidate and represent all this information in a precise manner. So these design solutions can then also be further augmented with advanced design solutions, again depending upon your requirements, where you want to do complex analysis with ease and assurance. You can leverage the time series unified load flow, so you can solve unified AC and DC systems together, especially for renewable systems, motor starting for distribution as well as industrial systems, power quality for data centers, as well as other systems that are heavily dependent on power electronics, contingency analysis for T&D systems, reliability for industrial as well as utility systems, railway traction or E-track study, where you can simply take the electrical system model, combine it with GIS as well as the single line diagram, and then here perform a multi-domain simulation where we are doing mechanical and electrical simulation of the train movement as well as its impact on the electrical system at the same time. And by combining the DC system, you can then also bring in the uniqueness of having energy storage device or wayside storage as part of the electrical model design as well as the analysis. you can then perform additional advanced design studies like transient stability, where by a click of a button, we can also show you through a live plot what's essentially going on with this electrical system under various simulation conditions. And you can use it for very quickly identifying the critical fault clearing time, in this case where the generator goes out of step. And if you clear the fault quicker, what is the actual impact on the system? And is the system stable under that particular fault condition? ETAP also allows for additional complex studies such as electromagnetic transients, where you can also perform electromagnetic studies such as ferroresonance, switching transients, and many other types of electromagnetic studies directly from ETAP using ETAP EMT. ETAP also gives you co-simulation capability that allows you to combine RMS simulation through transient stability with the EMT domain into a single model. And that itself has its own set of advantages, where you can take a detailed model of a power electronic system and integrate a complete network along with details from the EMT domain and simulate along with the RMS domain. So this kind of gives you the best of both worlds and allows you to quickly perform simulation between ETAP EMT as well as ETAP transient stability. So this kind of summarizes our digital twin journey for advanced design solutions, particularly for renewables, microgrids, industrial, as well as low voltage systems, depending upon what the requirement may be. Now, when it comes to distribution systems, things are a little bit more unique. For distribution systems, we essentially have a few more analytical capabilities that are more unique when it comes to radial and looped analysis, where we're dealing with unbalanced network design. And the most basic calculation there is load allocation, optimal power flow, fault management, service restoration, feeder hosting or integration capacity analysis, line and cable constants, where we're determining the impedances of various overhead lines and underground conductors, overhead sag and tension of the lines, volt-var optimization, switching optimization, and optimal placement of capacitors, as well as network automation devices, voltage regulators, and reclosures in the system. So this essentially becomes part of the DNA analysis for electrical distribution systems. And when we are performing this analysis for distribution network customers, we're essentially leveraging the GIS as well as the single line diagram. ETAP essentially allows us to look at the GIS model of the electrical system along with the background map tiles. And within these background map tiles and the GIS diagram, you can also have an association directly with the single line diagram. And what we mean by that is whenever you click on a particular component on the one line diagram, that component can essentially be associated directly with the corresponding geospatial view. So every time you're clicking on a particular component in the system, ETAP quickly tells you where it exists on the GIS representation of the single line diagram. And this essentially helps you quickly identify not only where the component is, but also understand the connectivity within the electrical system. Whenever you perform calculations such as a power flow in the system, or any other design or advanced design modules that we essentially covered, the program essentially returns the results directly on the single line diagram as well as the geospatial diagram for ease of use and understanding. And again, these visualizations are the ones that are moving from design all the way into operations, regardless whether they're schematic or geospatial. Now, once our design is done and we're ready to commission the system, we have partial real-time data and we have all our design-based analysis ready, whether they're basic or advanced design. They're all done at this stage. And we are ready to essentially now bring in SCADA information that includes state estimation. We can leverage EProtect. We can then use this information to do predictive analysis, utilize software in the loop simulation approach, record the data for sequence of events playback, and also use it for an operator training simulator. So this allows us to verify and validate the design model that was put together using complete or partial real-time data, and essentially move the model further along into its digital twin journey. So when this model is as designed, it essentially can interface with another ETAP and act as a software in the loop. And this essentially helps you when you don't have a SCADA system. You can validate certain operations with another ETAP design model and see the impact of making certain changes in the system, especially when you're energizing a system piece by piece. In this case, the system is not in normal operation, and it helps you understand the impact when you energize certain large assets within the system before you actually take the action in the system. The as operated model can then also work as an OTS, working with ETAP eSCADA or any other SCADA, where the simulated conditions can return feedback to the SCADA system and act as an operator training simulator. The same system can then extend into the actual field devices, where you're not just generating synthetic data and collaborating with the ETAP model, but you can bring in the actual operating state into the SCADA system and then do the Whatif applications in an operator training simulator environment, in which case the SCADA changes are not really sent out to the field, they're actually used for operator training. You can also then use the ETAP SCADA or any other SCADA with this as operated model to further send the control signals out into the field if you are satisfied with the response of the electrical system. So again, the ETAP model evolves as either a connection to the ETAP SCADA or any other SCADA, and then interacts with the field devices. The operator training simulator can be in a standalone environment or a team-based environment. So let's take a look at the operator training simulator in action. The instructor can send a simple signal to the operator on their HMI, asking them to isolate a transformer from maintenance. This is a message from the trainer. So the operator can then go ahead and take the action as he normally would in the field. And as soon as the action is taken, certain alarms or events may be generated based on the simulation, which are shown on the bottom here. And then based on the alarm that's generated, the operator can continue taking further actions to isolate this transformer. And then once the isolation is complete, the topology shows that this transformer is completely isolated, and whatever alarms may be associated with it are displayed very clearly. Now this can then act as a training, or it can act as actual signals that can then be sent to isolate this transformer, knowing full well what the impact is going to be. You're not just limited to the single line diagram representation within ETAP. You can also utilize the SCADA visualization itself in order to have a better understanding of your environment. A SCADA HMI, including the generators and the rest of the system, could be more simplified and may either represent the ETAP SCADA or any other SCADA system, in which case you can select the generator, in this case, that you would like to manage in an operator training simulation environment, look at the real power dispatch on the machine, and then raise or lower the set point of the generator. When this happens, ETAP essentially simulates what would be the impact of increasing the power output of this machine by simply running the simulation in the background. As far as the operator is concerned, they are utilizing the full electrical model and visualizing the impact of either raising or lowering the set point on this machine. So in this case, we've gone ahead and lowered the set point on the machine, and you can do the same thing for voltage, frequency, or any other parameter. The operator also has the visualization of the time series data. What is the impact of changing the megawatt on that particular machine as they lower or raise the set point respectively. And they can do this for any machine in the system with full confidence of the simulation model in the background. Once we have successfully commissioned the system, that digital twin model can not only be used for an OTS, but it can essentially absorb or consume real-time data on a continuous basis to act as an eSCADA along with state estimation. We can then also do predictive simulation, forecasting, load management, generation management, relay asset management, forensic analysis through event playback, and of course the actual live OTS with the SCADA environment in place. So you can have the OTS again in commissioning mode, and you can have the OTS in power management mode as well. So let's take an example of how the state estimation and the load flow prediction works in ETAP. The electrical single line diagram represents the complete system picture. You can actually zoom in and see different values shown on the single line diagram. You can zoom in and see the actual values shown on the single line diagram, such as the measurement data, which is coming from the actual field or from any other SCADA, and those values are shown in white. And they become part of the electrical single line diagram that was used for design basis. The state estimator values are shown in red, which are telling you exactly what the power flows are throughout the system, especially in areas where we don't have any measurement. And this is done on a continuous basis. You can also then go ahead and look at the deviations, which is the difference between the measured value and the estimated value, and observe and tune the model such that the estimated value is close to the measured value. The reason you would do this is so that you have better prediction when it comes to validation before operation. You can simply switch over to another visualization, and remember, I mentioned earlier that you can have unlimited views. So one of these views is in simulation mode, where you can capture the real-time data, a snapshot of it, and run your power flow simulation and see the operating alerts based on that design model. But this design model is enriched with real-time data. And then if you open a breaker in the system and run the simulation, you can see the impact of opening that breaker in the system. And in this case, we are overloading this transformer if you do that. So essentially, we are predicting the response of the system, knowing the details of the model, and having the situational awareness of where the system is operating at this moment. The simulation is not just limited to simple load flow calculations, but the entire suite of ETAP design and advanced design solutions, as I mentioned earlier, is at your disposal. So you can switch over once again to any simulation presentation or a parallel visualization of the electrical system. And now I want to perform a motor start. As an operator, I want to understand the impact of starting this machine in my electrical system before I actually start it. So you can essentially take all your existing scenarios, all your existing analysis that was previously done, get online data and run your scenario, or simply go to the motor starting module and perform startup of a particular machine. But let's say I want to do a startup when my substation breakers are open. Can I start this machine successfully if I'm isolated from the grid? So you can simply go ahead and perform the dynamic motor acceleration analysis, see the violations if there are any, or any overloads of any existing generators in the system, and plot the results directly as an output or an outcome of your simulation. And in this case, we can see that the machine actually takes about 4 to 5 seconds to start up, and it does start up successfully. However, are the violations within permissible limit? You can essentially go ahead and see those from the alert view. You can get that online data at any point in time and repeat that simulation again. So in summary, that ETAP Digital Twin goes from ETAP being in offline mode, where you're doing design analysis, into real-time operation mode, where you're leveraging the real-time data from SCADA system. And you can then take that entire model into electrical monitoring and control system HMI without replicating or redoing that information or recreating that diagram again. And you can take that model into OTS mode, where you can essentially do a operator training and essentially as SCADA operation as well. So that single digital twin essentially is reused multiple times in different domains or in different phases of your electrical system. Another advantage of using the digital twin and connecting it to assets in the system is EProtect. EProtect allows us to essentially get all the protection relay settings into a centralized relay asset management database. It takes the as found settings, which take a long time to collect from the field. It does that on a continuous basis by polling the relays and making those relay settings available to your design and analysis workstations. For those of you who do protection studies can see the value immediately, because a lot of time is spent collecting this data manually and populating the selectivity analysis in an accurate manner. And selectivity is important in ensuring that the system remains reliable and resilient at the same time. When the relay settings are made available to ETAP star or ETAP star Z, protection and selectivity module for overcurrent and distance protection, you now can do your sequence of event analysis directly within ETAP star. If the sequence is not correct, you can optimize the settings and send the optimized settings back to EProtect, go through a workflow process and approval process, and then potentially update the relay directly, or write a setting file that you can update the relay by essentially uploading the settings directly into the relay. From the relay, we also get fault waveform, which can then go inside ETAP for fault location and fault identification analysis. And the fault location information is also available inside EProtect as an outcome from the digital twin model. You can also send the as operated sequence of how the breaker stripped in a particular fault event into ETAP, and then compare the as expected versus as operated system. And then you can diagnose, did the relay operate adequately or not? And all of this information is then available through the ETAP web clients as well for you to visualize the information. So the design and analysis workstations allow us to take the equipment modeling, perform system analysis such as sequence of operation, and you can also use it to do asset tracking on your GIS. The EProtect system gives you the central relay database for grid compliance. It gives standardized setting processes and also gives you a substation hierarchy model so you can find the relay with the same name in multiple substations very quickly. And this not only includes the relay information, but can also include complete substation info such as breakers, CTVTs, batteries, and other settings. The web client gives you an enterprise secure access into the maintenance and operational history of the relay, and also acts as a portal for the health monitoring of your substation assets, and also includes additional applications such as fault location, phasor measurement unit information, and also is a driver for the workforce management to essentially allow the crew to go ahead and investigate the issues as well as the safe maintenance of the electrical assets. So ETAP in summary solves all the common sources of design errors by streamlining and making an integrated project execution, and this is enabled through NetPM and our multi-dimensional database. It eliminates engineering assumptions and provides electrical reference of components through a verified and validated nuclear library, so you can have data integration with other systems such as BIM, CAD, IEDs, relays, and avoid any transcribing errors and stale data being present in your design model and your operations model, so that you're making informed decisions. It allows for complete analysis and a full spectrum of studies so that you can meet regulations and other standards. And it eliminates inaccurate or incomplete data by predicting every single possible action in the system. You can avoid possible failure modes that you have not anticipated. And this is done through continuous model validation to make more accurate decisions. One of the other type of power management solution is ADMS, which is very specific for utility distribution systems, where we leverage the DNA model or distribution network analysis model that is predominantly geospatial based and provide DMS applications, OMS, load allocation, FLISR, switching optimization, DERMS, volt-var optimization and control, and of course a dispatch training simulator to make a end-to-end ADMS solution that is leveraging your design, or planning model. We also go through a distributed automation journey where the electrical control system is augmented by economic dispatch, automatic generation control, intelligent load shedding, microgrid control, nanogrid control, power plant controller, and also leverage hardware in the loop wherever necessary to essentially validate the system and complete the end-to-end distribution automation journey. So let's take a look at ILS in action, where we once again leverage the ETAP Digital Twin model to understand what would happen when there's a trip in the system and what impact does it have to my intelligent load shedding. The impact essentially is felt through a trigger that is received by the load shedding system, and a load shed priority table is generated as an outcome of that trip in the system. This trip is not only looking at the topology, the connectivity of the system, but also the operating generation and load levels. So you're no longer left with a static priority table, but through every contingency, we are generating a dynamic priority table that meets the stability requirement of the system. And that's key. It's not just looking at the delta of power generation and load as an algebraic equation, but it's looking at the dynamics of the system to understand what loads need to be shed that are non-priority loads in the system. And as you can see, we're doing this for every single possible contingency in the system in parallel on a continuous basis. And this is done in anticipation of the event. Therefore, makes ETAP ILS a proactive load shedding system that's contingency based and uses dynamics to essentially determine the load shed tables. So in conclusion, the ETAP solutions provide safety and protection of people and assets to prevent electrical shock and ensure overall protection, so that you can also then recover from outages that you can not avoid in the system, restore power safely, and avoid electrical fires. The solution allows for reliability and business continuity by increasing electrical asset and system reliability and lifetime, and avoids disruption by preventing failures of the electrical system and minimizing the impact felt by that outage. We also simplify regulatory compliances by identifying, evaluating, and validating the compliance requirements, either in design mode or operations mode, and we maintain these compliance obligations and our commitment to the stability as well as the emissions reduction overall. So the unified multi-dimensional digital twin platform gives you the capability to do design with smart visualization. It's rule-based. Integrated network analysis modules give you a full spectrum capability to analyze any system in any domain, whether it's electrical, thermal, electromagnetic, and it allows for collaborative engineering, accelerating your design, project management, as well as intelligent analytics or conclusions that are generated by the program itself. That same digital twin model moves into operations. So it gives you that base for monitoring and creating pseudo measurements. It allows to become an operator training simulator. So it gives you that operational awareness. The predictive simulation gives you the validation before you operate that system. And then you can automate the system by having proactive controls that have been used already during the design stage of the electrical system. Another example of that is the microgrid control that we can visualize very quickly. In this particular system, we can see that we have a microgrid controller available. In this microgrid controller, we've already selected our logic, and then we are able to actually define the parameterization of the microgrid control system. The advantage of doing this, again, is once the design is done using this parameterization, you can be confident that these settings would be the ones that are deployed out in the field, which allows you to not only mimic the behavior of this control system under various different conditions, but you can also use it to essentially determine any possible issues that may have in the system before you actually deploy. So therefore you can bring in the automation logic within the design itself and simulate different what if cases in the design environment and take the automation logic through this model and apply it in your actual control system. And in this case, we are essentially varying our wind turbine wind speed and power output over a period of a day. The PV output is varying over a period of a day. And same thing with our loading, which is not constant. It is also variable. So therefore, we can see what the energy storage dispatch looks like and what is the point of interconnection power exchange at the point of coupling or the point of interconnection in this case. So in summary, the ETAP Digital Twin can go all the way from design to operation and automation of the electrical system. Thank you.